Sample preparation is very complex. It's very diverse because you have different sample, your project is different, your budget, and your research goal. You can see this is our lab setup. There are different devices there. They have different setup for different sample preparation. It's very time-consuming, labor-intensive, and you need experience and skill for different sample extractions and preparation. And sometimes it can be expensive because if you add it up with internal standard or you buy authentic standard to confirm your final structures, the cost will add up. And of course, sometimes you can see the students doing the sample preparation because it's very boring, it's physical, but it's very, very important. It is the foundation of your success of your project. So I'll talk about these different ideas, give you a basic concept what involving sample preparation. Involving your idea, which is coming from your lab, and how sample is handling, which previous speaker has already said, internal standard, text mixture quality control, and some basic extraction procedure and chemical modification. Finally, a few our current practice of how sample are prepared for LC and GC analysis. This is just a graphic representation of workflow of metabolomic application in our lab. And you can see this is, You have an idea and a sample preparation right in the front of early stages. And then we go to instrumentation analysis and also data analysis, which other speaker talk. So the key is the sample preparation is a crucial step. And sample preparation, mass spectrometry, and data analysis is all coming together. And if you search the three words, and you will see there was exponential growth during the a decade. And but the review of these procedures is not a whole lot. The key of the exponential growth of these research papers due to the analytical technology advancement, especially the LCMS. LCMS is a whole new technology that can talk for days. So the LC technology really enhanced all the biological application, including metabolomics applications. Sample preparation is very complex because we're dealing with many different subjects. Here we're dealing with lipidomics, metabolomics, and sample sources are very different. Here in our lab, we're dealing with human sample, animal sample, and type are different, cell, biofluid, and tissues. And also dealing with different instrumentation because instrumentation needs requirement of different sample preparation method, especially GC and LCMS. And also depends on research goal. You could have a targeted research with untargeted. You could have a quantitative with a qualitative analysis. Or you have a small set of sample versus a large long-term research project. This will define the sample preparation. The goal of sample preparation is that because instrumentation cannot take your sample as you collect it from human or tissue, it has to be transformed or prepared properly so the instrumentation can take it and into the instrumentation to measure physically. And sample preparation must be very effective and high quality in each of every step so that the end result of sample preparation can be reproducible day after day or experiment after experiment. And sample preparation can give the analyze the power that when you shoot the sample instrumentation, you can review the targeted compound you want to see, not the other interference that you don't want to see. The result is sample preparation. We want to increase our targeted compound concentration because the dynamic of the analyze could be very, very large, like E10 or even 12. So your analyze could be very small in concentration, so we must increase the concentration. We also want to increase the purity of your targeted compound. The next one, we want to reduce the biological matrix or interference like salt or proteins that will affect your detections. And sometimes chemical modification has to be taken because we want to increase in the detection limit, we want to increase in the LC separation resolution, or we want to increase in the GC volatility so it can be analyzed by GC. And the sample must be carefully prepared, free of particles and other interference to get into the system to be analyzed properly. These are the typical samples we experience in our core facility. Cell culture is a common one from human and animal tissue as well, and biofluids, plasma, serum, urine, saliva, and CFZ fluids. Other type analyzed like feces from animals. So you can see these are all different samples. They need different methods, extractions and treatment to convert them properly into a sample that can be shown on instrumentations. Biological samples are easily degraded because they coexist with enzymes. So when you get out of your animal model or human subject, they are subject to enzyme degradation. And also the high temperature during your shipping and during your handling could affect your concentration of a sample. Another factor is oxidation, that during your exposure to the air or to the solvent. So these all must be taken care of. So please pay attention to your sample environment and conditions, because your sample conditions really determine how sample preparation goes and how your final results will be. So please ship your sample in a dry ice. That's the best way. And we will store your sample in -80 immediately. And we will minimize the cycle of freezing and thawing so that only one cycle is needed for the sample to be prepared and injected in instrumentation. And prepare the sample in a minimum temperature like ice, and shorten the time of handling the sample and prepare the sample, so minimize degradation. Be consistent is the most important step in sample preparation so we can get consistent results. There was a very important concept called internal standard. So internal standard basically is a compound that not exists in your sample. It can be man-made, usually it's a man-made compound, or exogenous to your system. And the best internal standard is the C13 or hydrogen deuterated compound. Here is our is a two sugar analyzed. You can see that right here that these are total ion chromatography, and these are the sugar of target, and these are internal standard. So that the internal standard is used, I'll show you next slide, is used for quantitation, adjustment of all the parameters, efficiency of extractions. The best internal standard is the analog of this isotope because they have exactly the same chemical properties. They will elute at the same time, they will have the same ionization efficiency, so you will not lose anything in terms of a true representations of your target compound. And this is just an example of quantitation using internal standard. So internal standard is a measurement of differences due to the sample preparation. When you do sample preparation, you're always losing something. But internal standard, since you add a known amount into the system prior sample preparation, it can actually correct any losses of sample. And you can correct any efficiency of extraction processes or losses like filtering, like transfer. In addition, the internal standard can measure the mass accuracy, the correct retention time, and ultimately the internal standard is for quantitation. For untargeted analysis, if you measure thousands of compounds, you cannot afford to buy 1,000 internal standard for 1,000 compounds. So in that cases, a subclass of internal standard can be used for a whole class. Another compound we use for sample-based test mixture. And test mixture basically you buy from a vendor or you prepare yourself, and when measured, the performance of your GCLC instrumentation and see if there's any degradation of your column. Is ion source is dirty? So it's basically make sure your instrumentation is performed, should be before you analyze your sample. And here it is, for example, you can see the retention time, you can see the mass accuracy, and before you analyze your sample. Quality control is a very important concept. Quality control sample usually is a mixture of all your sample put together. So it has all the components you want to analyze in that particular QC sample. So it's a true representation of all the metabolite you study. And if you analyze, say if your project is 2 years long, you analyze thousands of samples, then we have to buy a QC for you because you cannot combine 2 years sample all together. Other quality control, including the replicator blank, negative control, and the solvent control. And you can see usually the quality control was injected very first and then in the middle and the end of the sequence so that you can measure the variability of the system. So the quality sample basically is for condition your analytical platform, your column, your system. So make it like exercise the system before you inject your sample. And you can use for data quality assessment for QA. It can determine your reproducibility of your sample batch, give you like ISD or mean CV, so you can measure how variable your data is, and you can correct the signal variances. Next, I'll talk about some general technique we use in our laboratory. One common one is called solid phase extractions. It is a chemical extraction and a separation procedure. The main goal is to concentrate and isolate the metabolite you want from the interference you don't want to see. So it is an interaction between a liquid and a solid solvent. And there are so many different compounds to be chosen with, so it's a very, very effective way to separate your compound or concentrate compound from your matrix. The good thing about the solid phase extraction is that it is one-time use, it's very affordable, and it can be automated for a large set of samples. And we have that device in our lab. You have 1,000 samples to do it. Usually we do that in a small set. Large set is possible. Why we do solid phase extraction? Because solid phase extraction, first of all, will eliminate the interference. For example, you want to see the compound 1 here because of the background of the matrices that the peak 1 is not fully detected. However, if you're using eloquent solid phase extraction, you can see the color will become colorless, and there was a very clear signal to noise peak for detections. The solid phase extraction can also increase your sensitivity because if you're starting with 1,000 microliter and you concentrate it and with 10 microliter, you have 100 times increase your concentration. So it's a very effective way to increase your sensitivity. You can also decrease in the suppression. For example, protein precipitation is not enough to get rid of the suppression. Solid phase extraction can remove further compound interference, and your signal is much stronger, which means your data quality is increasing a lot. The next technique is liquid extraction. Basically, it is aqueous and organic phase extraction, and partition between these two phases are two types of compounds. Either is aqueous dissolved or organic phase dissolved. These techniques are very widely used in lipid molecules. And liquid extraction is a very effective way to remove salt or extracted organic compound from the aqueous phase. It's very fast. The extreme is the sugar is 100% dissolved in water, and fatty acid is 100% dissolved in chlorophyll, for example. So they can completely separate. However, there are some metabolomics or small molecules that have some interference. So you always leave a small portion in one phase, but you can extract majority in the other phase. So there will never be a complete extraction. Just keep that in mind. Chemical modification metabolomics sometimes are necessary because we want to increase in the sensitivity of our detector, which is mass spectrometer. We want to increase in the LC resolution so they can separate more effectively. We want to convert a compound, which is non-volatile, into a volatile format. So it can go through the GEC, because the GEC you are starting like 80 degrees and end up with 300 Celsius. So you need the compound to be stable and volatile. So these are the three goals of chemical derivatization. Here's an example that Dr. Kennedy in our core and chemistry, their group developed a very elegant chemical derivatization and the quantitation method to analyze these neuron transmitters. These are 17 compounds. They are very difficult to analyze because they're very polar. Their LC resolution is very poor. They're not retained on C18 column. They're difficult to quantify. So they using a universal benzene chloride derivatization method to convert a compound into very hydrophilic form into hydrophobic form. So they can behave very well in the C18 column, and at the same time using the isotope isomers of the reagent, they can label each and every compound with the C13, so they can do quantitation simultaneously. Here you can see just 8 minutes, they can separate all 17 compounds in very sharp peak, which is in high resolution of LC, and also increase the sensitivity, increase the LC resolution, increase the sensitivity of detection, and they can do quantitation because they can simultaneously using the C13 derivatized isomers, and they increase in the throughput because they are shortened the analytical time. So one derivatization can give you multiple benefits. These are the general sample preparation procedure. The simplest one is dilute and inject. So we don't need, for example, some urine sample. We just need, when I work in a company, they just do a dilution, dilute the salt and maybe protein content and analyze a drug, so they can just do that without any chemical extractions. Or they can just dry that and derivatize directly, go to the GCMS. And most of biofluid, like for example, serum chlorine, the initial stage is protein precipitation because a large amount of protein into the serum sample or plasma sample, they can easily clog our system. So it has to be precipitated to remove 100% maximum if possible. And cell and tissue, you have to homogenize first, of course, because you have to homogenize, break the cell before you can do extractions. And the final step usually is the solid phase extraction or liquid extractions. And this is just example of a GCMS. For example, it's a human plasma. We must remove the protein by organic solvent precipitation, and then remove the precipitation and dry the sample. Then we using the methoxamine and the TMS to protect the functional group. So the OH become OH TMS, so the compound become volatile, and then you can inject into the GCMS. This is a typical example that our targeted group using amino acid. You can see the first step is to add internal standard, and then you clean up using C18 phase, and recovered the C18 from the C18 solid phase extractions. Then you add the reagent to convert the amino acids, the functional group, these two functional group into an organic functional group so that they can volatile under high temperature and stable. And finally, they extract it with amino acid and its internal standard and dry and redissolve in a solvent like acetone or hexane to do GCMS. For untargeted LCMS, the front-end sample preparation is very simple. It just basically you want to extract as many metabolites as possible. So all we need to do is do protein precipitation because we only limited our molecules into smaller one, which is 1500 below, and dry after precipitation and centrifuge. We dry down and we dissolve into appropriate solvent, usually is the water and a little bit organic, and into the LCMS, either C13 or Helix column. These are protocol that we practice now in our current Untargeted platform. We have a cocktail of acetone, acetonitrile, methanol to precipitate a protein, along with adding the internal standard in the very first. Then we do the precipitation in -20 overnight to make sure protein precipitate completely or as much as possible. And then we remove the protein and dry the sample and redissolve in the proper solvent and go into the LCMS to do analysis. As I said, the tissue sample, if you submit a tissue sample, we usually have to do a homogenization process. Usually we wash the tissue to get rid of any blood coming out from the tissue sample. And here is it is a bullet tissue grinder that we just recently got. And you can do one-step extraction just using organic solvent of your choice to target either the organic soluble or aqueous soluble solvent. Here I show you two-step. Is that you can first using a cold solvent of methanol water, and this only extracted very polar metabolites. And after extraction, you go through this procedure and get your sample. This is called aqueous extraction. Or can then the solid precipitate can do further extraction with a high content of organic solvent. So this we call organic extract. Or you can do just one step. And I'm sorry, got the wrong one. Then, okay. So we will demo this extraction today. The last type of sample is cell extraction. The cell is usually grow in a median, so the goal is to remove the medians and other contaminant between the cell and to get a very clean cell and then crush the cell and extract the content inside the cell. And the goal of this procedure is to try to reduce the cycle of extraction and increase the sensitivity and reducing the preparation time. So this is done again with Dr. Kennedy and other group in our core facility. They developed this particular method for cell extractions. We'll show that I do today. The idea is try to do a very rapidly crunching, just a snapshot to stop the metabolism at a certain time point, and to remove the interference as much as possible, and to extract a broad range of compound, and of course to preserve the liable organic molecules. And the current method is not ideal with literature because they're very slow, complex. They have extreme pH and they're not LC friendly, and many of them are not validated, and recovery is not validated. So the work was done by a candidate group. What they do is that they examine the major issue like solvent content, extraction time, number of cycles to tackle the fundamental of these fast extractions without losses of efficiency of extraction of most of the component inside the cell. Here's a show is that the cell coming up, they rapidly wash the cell a couple of seconds, one time is enough, they find. Then they crunch the cell, break the cell, and they store the cell is -18. Once this is ready to be used, they can extract it with a mixture of solvent, 9:1 ratio of methanol chloroform plus internal standard, and then they break the cell, and then they transfer to precipitation and analyze the small molecules. So the whole process is just 4 minutes. And this all can be done in the amphitheater after you transfer that. And multiple extraction and multiple washing are not help for final recovery. So one time is enough. So this is increasing the efficiency of extractions and turnover time dramatically. So we will demo this in the afternoon, how this works. Well, in conclusion, I say the sample preparation is probably the most important step to ensure your success of your project. And the most important concept is that sample preparation should be reproducible and must be comprehensive. And it is the foundation of any analytical analysis, especially metabolomic in human or biological science. We should understand that each sample preparation is very unique because your target is different. Your research project is different. Your molecules is different. So each method is tailored to a specific need, and it must be developed and optimized and finally validated so that we can analyze your sample in a reproducible way. And then I hope that this serves as a starting point that to give you an idea how sample preparation represents in our whole flow of metabolomics. Come to see us so we can discuss the specific your need. And I'll give you some references so that you can go through. And finally, I think this is a breaking point. Could you please fill out these 3 presenters and give them to Missy before you leave the room? Any questions I can answer for you? Any questions? Yes.
You recommend to rinse cells with water, 10 milliliters, blah, blah, blah.
Yeah.
But it should cause osmotic effects and actually changing concentration of many metabolites, any even transport of some osmolytes from cells to outside medium. So I think this method can interrupt metabolic profile dramatically.
Well, it is very fast. It is a couple of seconds watch, quick watch.
Seconds is enough for transport.
Right. So in this particular study, if you look at this particular study, they looked at that specific question. So this was done as a targeted analysis.
Maybe it's okay.
PCA cycle intermediate. So you bring an important point in that you probably need, if you're working with a different cell type, you probably need to do this yourself to make sure that this actually works well in your case. But this was a targeted analysis of just glycolytic PCA cycle intermediates, which are not really diffusible. So you were looking at a cell population, looking at a target group of metabolites that are actually not prone for the osmotic changes that you are seeing. But if you are looking at something else that actually are useful for that, you need to do preliminary experiments to make sure that is actually appropriate in your cell.
Well, it's just wondering, shouldn't it be proposed like a standard method?
No, this is for our targeted analysis. So this is what we do for PCA analysis. So this is our core procedure for the PCA analysis. That's meant only for